what information we need for cities to evaluate the urban risks of for example, firstly, we need the background climate information of cities. It's a and a larger scale of cities. We need the background information that including the global warming, sea level rise, the extreme precipitation, like the 95, 95 percentile of daily precipitation, and the storm frequency, which uh, results in heat streaks, coastal flooding, river flooding, uh, drought, and wind. And also, we need the intercity, intracity informations to like the urban heat island, population emission, precipitation enhancement, uh, and the portion of impervious surface cover inside city, and to evaluate heat streams, air quality, and pluvial flooding, which are directly related to the impervious part of city. Our research aim is to evaluate the based on the all the available worldwide data sets to evaluate urban risks uh, in all the large cities whose population is larger than 100 or than 1 million, and to create a metrics of urban risks to facilitate the knowledge share and to compare urban risks in different cities. We need a consistent description and evaluation of urban risks worldwide. That's my method. Firstly, we identify the urban informatics that we need for cities. Um, we need the natural context of city. We need the occupation pattern of city, which including the future climate, the topography, land cover of cities, that's natural context, and the river network. And we need the occupation pattern of cities, which including the population distribution and the distribution of urban infrastructure. Here we need the LCD maps to describe the urban infrastructure. And in details, we use the data sets here to extract information mentioned before. We have the DEM, which uh, provides the elevation, and we have the geomorphology data. We have the coastline to analyze the proximity of city to river. Oh no, sorry, to ocean. And we need the CMAP6, which is the future climate. And when we have the river flood risk and current normal climate probability, and we have the population. We have the global human settlement layer, and we have the global LCD map, uh, greenhouse gas emissions. That's all our data sets. And based on these data sets, we analyze the pluvial flooding, coastal flooding, river flooding, and the heat streams, and the energy demands described by heating and cooling degrees. And the analysis, we use Guangzhou as an example, and analysis for Guangzhou was applied to cities worldwide, but we choose Guangzhou as an example and show the information about big cities. This is a detail and the description of the all the data sets we mentioned before. Uh, The main obstacle of this study at this stage is the data we mentioned before. We have big data volume, and we have to manage processing, analyze, visualizing different different data in all kinds of formats, and we have achieved this with help of Google Earth Engine and Python, ArcGIS, ArcPy. This is an overview of our dataset. Uh, this is a local climate zone and global. This is a distribution of all the millionaire cities in the world. And we have some basic statistics of millionaire cities and their climate and their climate type and their income level, high income, upper medium income. And this is an example of Guangzhou. This is a Google Earth map of Guangzhou, and we have the population, elevation, precipitation. That's a overall overview of Guangzhou, and we can extract the this information from CMap. We can see how the daily maximum temperature and the precipitation changing of Guangzhou. We can see the during the we can expect the similar precipitation in the oncoming 100 years, but a significant rise of temperature. And this is a map we have Guangzhou, and this is a statistic of the distribution of population in Guangzhou. We have compact LCD 123 account only 10% area of Guangzhou, but accommodate more than 20% of population. And this is analyzed on the the river flooding risk of Guangzhou and current climate probability. And when we look at the flooded area, only the flooded area, there are a small portion of in this area are compact LCD, but this part of urban infrastructure accommodated a huge part of population, which means the proximity of compact LCD to river could lead to a huge exposure of urban population. And also we do the analysis for coastal flooding. Coastal flooding is analyzed by using the elevation data, future sea level data, and the surge and tide data. And so we do the similar analysis. How many compact LCD area are of influence and and how many population is in here. And this is a urban climate type of big cities and the income level of it. Every city is different. And we can look at the climate change pattern of large cities. We can see the daily maximum temperature is going higher for almost all the city, but and some of them is experiencing a rapidly rising in precipitation, but some of them have smaller precipitation, which lead to different type of urban risks. And this is a changing daily mean temperature and the energy demise in percentage. The energy demise is represented by heating and cooling degrees. And we can see in the cold area cities, they are experiencing they will have lower total energy demands for cooling and heating, and for the cities in higher temperature, it will need much more energy. Okay, and you can see the proximity of compact LCD to river and coastal could lead to high risk to flooding, but could have the potential to cooling because we can use the green and blue infrastructure more appropriately. That's all. And let's see the first examination of our project and the further step, including to include more types of risks and develop the integrated metrics for.
Then I could take just one question. Somebody wants to ask one? Our speaker? Right. See what I'm doing.
Thank you for your presentation. It's an amazing effort to do all this data. It is great. What will be the final resolution of this data? It will be the same, the resolution in of our
The main framework of this research is the global LCD map. So we use the same resolution as the global LCD map.
100 meters.
Yes, yes.
Okay, thanks. Now,